Hi, my name is Eric Tim, and I'm here to do an experiment that will test my theory of temporal quantum relativity against Albert Einstein's theory of general relativity, specifically how gravity works. You see, this is a Michelson Morley experiment, and as Michelson Morley experiment has been done in the past, it has always been gravitationally flat, which means, if I'm right, the reason we gravitate towards the Earth is because our frame of reference for motion is accelerating in the opposite direction, giving us momentum in this direction and causing time dilation because we're moving relative to space. And if I'm right, the reason why it never measured anything in the gravitationally flat surface is because it's perpendicular to the flow. And just like trying to measure the flow of a river, you can't do it from bank to bank. You're not going to measure a difference. You have to go parallel to the flow. You have to go upriver and downriver. And in this case, that would mean turning the experiment in the vertical orientation, which I've made this capable of doing that. But first, I want to do a control experiment showing you that I'm going to receive no difference in the horizontal just as Michelson Morley did it. Then I'll tip it in the vertical to do the experiment. Let's do it. Now, as you'll see in the picture, from the camera's point of view, it's looking at the fringe patterns and there's no movement in the patterns as it spins around. And when I take the apparatus and spin it the other direction, it only vibrates due to me touching it because it's very sensitive. But this proves that the apparatus is working correctly because I'm getting the exact same results that we saw with Michelson Morley. Now I'm going to tip it in the vertical orientation and do the experiment that tests my theory. When I tip it in this orientation and I begin to move it, you will see that the fringe patterns do move as it goes around the circle. This would suggest that I'm right, that the reason why we gravitate towards the Earth and it goes in the opposite direction, and the pattern reverses its orientation, moving just as it would, just in the opposite direction. This suggests that we are actually in a flow of space outwards from the Earth, which would be why we receive momentum towards the Earth and time dilation because of this motion. Now this has larger implications because if you are moving relative to space, but you're not moving relative to another observer who's receiving a different flow of space, for example, someone who's on the ground floor and someone who's at the top of a penthouse in a skyscraper is going to be receiving different rates of time, but they're not moving relative to each other. In what way are they moving differently? That would suggest that it's about your motion relative to the four dimensions of space that determines whether or not you're receiving time dilation, which means the relativistic behavior of special relativity is wrong, that not every observer gets to decide whether they're in motion or whether they're stationary. And this means we have another opportunity for an experiment to test my theory of temporal quantum relativity. However, this experiment is going to be rather expensive, outside of my budget, and I need the help of professional scientists to make sure that I do it right. And that was where you come in. I need you to spread the idea, and hopefully we can raise enough awareness about this concept that we can then move forward on that experiment. Now, if you're interested in reading more about how this really works and how it explains how quantum mechanics works, you can read my book called Temporal Quantum Relativity, and you'll find the links in the description. I thank you for your time, and I hope you can help. Thank you.